In the last few sections, we talked about the idea of sequences. However, in this section, our goal is going to instead be to focus on the idea of a series, and very specifically here, an infinite series. Now, sequences are going to be a very important part of this discussion, as we'll see here in this first video. But let's take a look at this opening definition that we have. A series, specifically an infinite series, results when we want to add up all of the terms of a sequence. So as I state down here, if I have a sequence that goes 2, 4, 6, 8, 10, then that is again just a list of numbers, sequence. But a series results again when I take those exact same values out of that list and I just start summing them all together. So let's take a look at some of the notation that we're going to use when we talk about sequences and their relationship to a series. So we're going to start by saying this, that when we write a sigma, remember that stands for a large sum, we're going to have I starting at 1 and going to n. This is going to indicate again that we're going to be doing an addition problem. However, what we're going to be adding are again items from a particular list, which we might mark with something like a sub I. And so of course, what this would look like is a number 1 plus a number 2 plus a number 3, and this would just keep going and going and going until I get to a number n, right? Because that's where the series here is instructed to stop. And so this series here would be considered a finite series. It stops after some time, right? There's only n items in that particular addition problem. However, when we write almost the exact same thing, again, an addition problem starting at item 1 out of this list, I might be able to say, well, how about we extend this addition problem forever? So when we write this, what we really mean is that I'm going to have a1 plus a2 plus a3, and then I guess on and on and on and on and on forever. This addition problem never stops. And so this is what we refer to as an infinite series. Now, our main goal within the rest of Chapter 5 is going to really be to focus on these infinite series and to really understand, do these series add up to anything? Can I actually go ahead and complete some sort of infinite addition? So this is kind of a funny topic, I guess, almost to cover in a Calc 2 class. It seems very, again, unrelated to the ideas of integration that brought us to this section. But the next time someone asks you what you're learning about in Calc 2, you can just say, we're learning about addition, right? We're just going to be learning here, how do I add infinitely many things together? Now, an important thing to note here is that this finite series here actually has another sort of a name that often goes along with it. If we have a series that adds all the way up to an nth item, that is known as an nth partial sum of the corresponding infinite series. So obviously, like here, I have a series that is an infinite addition problem, and if I stop at, say, thing 10, that would be a 10th partial sum, right? It's only a part of adding all the items, and I can specify which part, or kind of how far I made it. But this idea of a partial sum is going to become extremely important for us, because we have to start to define what in the world do we mean by an infinite addition problem, or what do we mean by saying that an infinite addition problem would add up to something. To understand that, we have to get into this definition down here at the bottom of the first page. This definition is unbelievably important. This definition is the foundation of everything that we will do for the rest of Chapter 5. This definition is going to be used almost every single video to describe what's going on. We're going to be constantly going back to it. And so it's really, really important that you understand this definition, that you spend time continuing to review it. I often joke with students that every morning when you wake up, the first thing you should do is read this definition, review it, think about it. Right? Like every single day that should be happening, because it's so crucial to understanding what happens here in this particular chapter. So let's take a look at what we mean by saying that an infinitely long addition problem could possibly add up to a specific value. Okay, so let's start by writing this. We'll say that given a series that maybe looks like this, we'll say it's a series a sub I starts at 1 and goes to infinity. How about we let S sub n, my color choice here is very intentional, this S sub n is going to represent or denote, oops, I'm going to let that S sub n denote the nth partial sum of this series. And so, what that really means is that when I go to and I say that I'm going to find S number n, you can think of that as like the sum of the first n items out of our original series. That would obviously then just look like this. I would start at item 1 and add until I hit item n. Okay, so with this S sub n defined, our nth partial sum, we're going to go ahead and state the following. First, we might be able to see that I could come up with, again, different values of this green S sub m every time I change the value of n. If I do S number 2, that's the sum of the first 2 things. S number 5 is like the sum of the first 5 things. But if I started increasing n just by 1 every time, I could get something like an S1, then an S2, then an S3, then an S4, then an S5, and so on. And that will start to look like a sequence where I have a first item, second item, third item, fourth item, on and on and on. And so what we'll say here is that if the sequence of S sub n, so if my sequence S sub n converges to a real number, for the sake of argument, let's call this real number capital S, so it's the grand total sum, it's what this sequence here converges to. So if my sequence converges to a real number S, that is, when I took the limit as n approached infinity of my green S sub m, and I ended up with big old capital S, then we will go ahead and make some conclusions about what's going to happen with this infinite addition problem. So here's what we say. If this green sequence converges to a real number S, we say that the series that goes from 1 to infinity, that is the series that we started with, we will give it the name convergent, and more than that, we say that this series, if it's convergent, we're saying that it's adding up to something. And specifically, we will say it adds up to this same exact S value that we had above. We can also say that S is then called the sum of the series, this infinite series. Okay, so this is what happens if I have this green sequence and it converges to a real number. I'll say that the series is convergent and that it converges to the same value as what the limit was here. Well, if it's the case that the sequence, again, of S sub n diverges, right? I mean, that's possible, right? I do the limit of a sequence and I get something that results in divergent. So if this sequence is divergent, then the series, this infinite addition problem, is called divergent. So we can see all these different pieces of terminology coming into play here. And we can see that there's a stipulation for when we will state that an infinite addition problem is going to add up to something, and when an infinite addition problem is not going to add up to something. Now, this definition can seem a little bit weird at first. Again, it's super important, but it will take some time to get used to. In the next video, we'll take a look at two different examples to try to at least start to understand how this definition really works, what it's really saying, and we'll start to look at this sequence of green S sub n's and realize that this is actually a very reasonable definition to form to understand how we would determine the sum for an infinite addition problem.